well, what's going to happen to the y values? It looks to me like the y values are going to get closer and closer and closer to 4. Again, take x coordinates a little bit smaller than 1, you're going to get y values that get closer and closer to 4, and that's going to be our solution. We would say the limit as x approaches 1 from the left of our function simply equals 4. That's all there is to it. Algebraically, what I would do is... Okay, so should I use the first formula, x plus 3, or the second formula, x squared minus 2x? Well, if I'm using x coordinates that are a little bit smaller than 1, that would be x less than or equal to 1, then I should just use the first formula. So equivalently, I could say the limit as x approaches 1 from the left of our function. It says that would be the limit as x approaches 1 from the left of the x plus 3. And again, now if we simply plug in the number 1, we'll get 1 plus 3, or we'll get the answer 4. So again, the same way to get the answer. Again, I think it's nice to have a little picture to go with it. Suppose, so the question didn't ask this, but suppose we were asked what's the limit as x approaches 1 from the right. Well, if we do 1 from the right, now, okay, I'm taking x coordinates a little bit bigger than 1. Okay, so if I use x coordinates a little bit bigger than 1, now I'm kind of sitting on the graph of the parabola. And as x gets closer and closer to 1 from the right, the y coordinates are getting closer and closer and closer to negative 1. They never actually hit negative 1, but they get arbitrarily close to it. So we would say the limit as x approaches 1 from the right equals negative 1. If the question had said what's the limit as x approaches 1, and they didn't specify from the left or the right, recall the limit from the left side has to equal the limit from the right side at a point for the limit to exist. And since we're getting different values, negative 1 and 4, we would simply say the limit as x approaches 1. In this case, it does not exist. Okay, so just to illustrate again graphically what's going on, algebraically what's going on, so certainly left-hand or right-hand limits can exist, but the limit itself may not exist. So, all right, I hope this example makes some sense. I'm going to sketch the other ones as well, and again, just try to talk about how you can, also use the formula, because eventually, this is really what you want to do, right? You don't want to have to sketch out every single graph every single time. Be much too complicated and much too time-consuming. So one more example here of doing a one-sided limit, and this one I'm not going to quite graph all the way. So we've got h of x equals the square root of x squared minus 25, and we're doing x is approaching 5 from the right. So again, we're looking at the limit as x approaches 5 from the right, the square root of x squared minus 25. Well, again, intuitively, I'm going to take numbers a little bit bigger than 5. So maybe, 5.1, 5.01, 5.001. So I'm getting closer and closer and closer to the number 5. So I'm bringing it in closer and closer and closer. Okay, so again, we're approaching from the right. Well, if I take numbers a little bit bigger than 5 and square them, as they get closer and closer to 5, the number that I'm squaring is going to get closer and closer to 25. And if you subtract 25, well, it's going to get closer and closer to 0. So basically the moral of the story here is this function would be defined for numbers a little bit bigger than 5, and we can just plug it in. We would get 5 squared minus 25, which would be the square root of 25 minus 25, which would be the square root of 0, which is just 0. And that's all we've got to do is just plug it in. Notice you have to be a little careful. If somebody said, what's the limit as x approaches 5 from the left, here I would say this does not exist. It doesn't really make sense to ask this question. Notice if you take numbers a little bit smaller than 5, well, if you square them, it's going to be a little bit smaller than 25, so that when I subtract 25 away, I would basically end up getting a negative number underneath my square root. And we don't take square roots of negative numbers. We're going to restrict ourselves to real numbers. And this would give us an imaginary number. So it wouldn't really make sense to plug in 5 from the left. Again, algebraically, if you plug it in, you just get 0, and you say, hey, it's 0. So these are things you have to, again, kind of be careful about. You have to really think, when can I just plug it in and when can I not? So again, here if I take something bigger than 5, it's going to be bigger than 25 after I square it. Well, if I subtract 25, I'm basically going to get something close to 0. It's going to be a little bit bigger than 0. But again, if you take the square root of that number, it's going to get arbitrarily close to 0. Okay, in this video, I'm going to do a couple relatively basic limit problems involving absolute value. And it's just really kind of one thing that you have to remember with absolute value to kind of get started. So again, in the first one, I want to look at the limit as x approaches 1 of absolute value x minus 1 over x minus 1. Okay, so of course, again, the first thing you try to do with a limit problem is plug in the value. But notice if you plug in 1, we'll simply get 0 over 0. For those of you that have seen L'Hopital's rule, well, I mean, I guess you could think about taking a derivative, but how do you take the derivative of absolute value? So we're going to talk about a slightly different way, just an algebraic way. And the thing that you need to basically remember, I'm going to first look at the absolute value of x. Remember, you can break up absolute value of x as a piecewise defined function. I'm going to break it up for stuff greater than or equal to 0. Let me make the first interval less than 0. And then I'll make the second interval greater than or equal to 0. For the second part, well, if you take a number that's already positive and you plug it inside the absolute value, you just leave it alone because it's already the correct value, it's already positive. But if the number you put inside the bars is negative, that's what the first condition says, it wouldn't be correct to say it's this when you break it up as a piecewise function, because, again, x is actually negative by assumption, so we need to tack on an extra negative. Okay, so the moral of the story is, when you have absolute value, you either basically just remove the absolute value, the bars, and put it in parentheses, or you put it in parentheses and you have to put a minus sign out front. Typically with these limit problems, that's what you have to do, is just rewrite it depending on, the limit. Okay, so notice again, the other thing I want to point out too is we break it up at the value where the inside is 0. Okay, so I'm going to do the same thing here with absolute value of x minus 1. I'm going to break it up. Okay, so notice if I break up absolute value of x minus 1, okay, well now the place I'm going to break it up is going to be basically at 1, because that's what makes the inside 0. So we'll make it less than 1 and then greater than or equal to 1. That'll be my restrictions on the domain. Notice if I take something, I'm going to do the second one again. Notice if I take something that's greater than or equal to 1, when I plug it inside of the absolute value, I'm already going to get a positive number, or 0. But basically that value I get would be correct. Okay, if I plug a value in smaller than 1 inside of the bars, it's going to be a negative number. So x minus 1 is now negative. I'll tack an extra negative in there to make it positive. All right, so that's one idea that we're going to incorporate into this problem. So, okay, again, we're interested in the limit as x approaches 1 of this absolute value x minus 1 over x minus 1. Well, notice our absolute value function kind of changes at x equals 1. And in general, for a limit to exist, remember the left-hand limit has to equal the right-hand limit. So what we're going to have to now look at is the limit as x approaches 1 from the left, and then we're also going to have to look at the limit as x approaches 1 from the right. If these are equal, the limit exists. If not, well then, this limit as x approaches 1 does not exist. Okay, so let's calculate this first limit, the limit as x approaches 1 from the left. In the denominator, we don't have to do anything. We just leave it alone. The whole question is, how do we go about removing the bars on the x minus 1? Well, if I'm taking 1 from the left, that means I'm taking values smaller than 1. And it says if you use x coordinates that are smaller than 1, you have to replace the absolute value with this first version, the negative version. Okay. So again, we're taking x coordinates that are smaller than 1. You have to replace the absolute value with the first version. And now we can simply cancel out the x minus 1. We would be left with a negative 1 on top. Remember, the limit of a constant is just a constant. So the left-hand limit is going to work out to be negative 1. We have to do the same thing with the right-hand limit. Again, in the denominator, you're just going to get x minus 1. In the, in the numerator, again, you think, what do I replace the absolute value with? And in this case, since x is going to be, okay, so now we're approaching x from the right. So we're approaching, we're approaching 1 from the right. X is approaching 1 from the right. So that means we're taking x coordinates that are larger than 1. So instead of the absolute value of x minus 1, it says we can just remove the bars. And again, I like to put it in parentheses, just, I think it's a good form. It'll keep you from making mistakes. Again, we can cancel out the x minus 1. You can think about there being a positive 1 left. So the right-hand limit actually equals positive 1. Well, since the left-hand limit doesn't equal the right-hand limit, our conclusion is that this original limit does not exist. Okay, so we can conclude that the limit as x approaches 1 of absolute